Thank you for staying healthy and come to next thing for today. So he is telling us about Jordan-Wigner duality for translational invariant Hamiltonians in linear data. Let's welcome Nat.
Thank you, Dubin, for the invitation to giving a talk here. So this work, I just happened to finish and put on the archive last night. So I'll be talking about some generalizations of Jordan-Wigner dualities to Hamiltonians in any dimension. So a little disclaimer is that these Jordan-Wigner dualities are usually 1D, but they've been generalized to a higher dimension by Kapustin. But today what I'm going to be talking about is how to generalize that even further to more or less get theories with, for example, fractons. And these fractons can be emergent fermions. So that's the interesting part, which we're trying to do. So let me start with I guess, epitome of 1D dualities, Z2 dualities. There are two very famous dualities that we know. One is the Kramer's 1A duality. So that is just you have a transversal Ising model, and you can map the operators from ZZ to X and X to ZZ, and that preserves the algebra. They preserve the commutation relations. And what this describes is a picture I stole somewhere from Supriya's website, which is you have a paramagnet and a ferromagnet, and then what I'm talking about here is actually at 0 temperature. So I'm just going to sort of remove that part so we only care about the lower part. So on one regime you have a paramagnet where all the spins are pointing to the right and excitations are these charges, and on the other hand, when ZZ is dominant, you have a ferromagnet and the excitations are created by domain walls. By the Kramer's 1A duality, you can swap the two, or basically visually it's sort of like this, not technically correct, but it's basically swapping the ferromagnet and the paramagnet. So you can, more technically, you swap G to 1 over G, but this duality allows you to exchange, and you can find that there's a critical point at G equals 1 in this case. Another famous duality is the Jordan-Wigner duality, which says that if I have this model for like a p-wave superconductor at the guitar chain, you can interpolate between the trivial phase and the Majorana phase, and there's a way to map between these spinless fermions into a spin chain. And basically, this duality tells you that you can map, for example, this trivial phase to a paramagnet, and map this Kitai phase to a ferromagnet. And if you want, you can do a Fermi-Kramer 1A duality to swap the two. So these 1D dualities are pretty well known. What I'm going to try to focus today is generalization of this in terms of Z2 dualities. So what do we know right now about current Z2 generalizations? So in higher dimensions, Kramer's 1A duality has been generalized. So for example, for 2D, if you have a 2D transversal Ising model, you can do a duality, and the resulting ground state, you can show that it's mapped to like a deconfined or confined transition of this from trivial to toric code. And in higher dimensions, you can also get transitions between higher trivial and higher dimensional toric codes. We also know that there are not just the case of Z2 zero form symmetry. We know nowadays that there are Z2 higher form symmetry. And we can also do Kramer's 1A duality to map between different form of symmetry. For example, in 3 plus 1D, I can get the 3D toric code by instead gauging not a zero form symmetry, but I can also gauge a 1 form symmetry. And the resulting theory is that you swap what it means to be a charge or a flux of the E charge or the M loop of the 3D toric code. At the same time, there's also another interesting symmetry that's emerged recently in relation to fractons, which are subsystem symmetries. So in that case, for higher form symmetries, we know that the symmetry is preserved on some closed lower dimensional manifold. But for subsystem symmetry, there seems to be like rigid lower dimensional manifolds, such as planes or lines, on which you can have a Z2. And it turns out that by Vijay Haah and Fu and other people, that if you take the symmetry and sort of gauge it, or Jordan-Wigner duality, what you get are these models with immobile particles known as fractons, which is because of some conservation of charge on these planes, you are not allowed to create, say, 2 at a time, but you need to create like 4 at a time. And these weird rules, it could also be planes, it could also be fractals, give rise to different interesting lattice models that for now we conjecture that they're beyond the scope of TQFT at the moment. So this is the Kramers-Wigner duality. They're much well known than Jordan-Wigner. So for Jordan-Wigner, actually, just for the higher dimensions, it's only been developed recently by Kapustin in this paper in 2017, which is in higher dimensions, you can do a duality between fermions to a spin system in higher dimensions. And basically, what you get is a spin system emergent fermion. So for example, if you bosonize the 2D fermionic system, you can get a 2D toric code. 2D toric code has fermions. If you do it in 3D, you won't get the 3D toric code, but you would get a twisted 3D toric code, in which the charge, the point particle, is actually a fermion. So these Jordan-Wigner dualities realize some weird gauge theory under which you can realize an emergent fermion in the spin system, and these gauge theories have some relation to the spin theory having an asymptote anomaly, in the sense that you cannot consistently couple this gauge field you can consistently couple it to a dynamical gauge field. So
that is true in every dimension, or only in even dimension?
For this work?
Yes.
This work in every dimension you can do a duality, yes. It's been done recently. So what I'm going to talk about today is try to motivate how to get...
Sorry.
Yes.
You're going to say, but can you remind me, when you say 2 is Z2 gauge theory, 3 plus 1 D case.
This one.
That one.
This is a twisted 2-form gauge theory.
Oh, 2 form.
Yeah.
So what's the twist? Topological
The
term.
twist is like a Steenrod square, BB. Yeah. In 3 plus 1.
Oh, 100. Oh,
Yeah. Right. I'm only talking about Z2, so I think it should be fun. Anyway, so what I'm going to be talking about today is how do we get this part, which realizes higher form Jordan-Wigner dualities for fermion systems with possibly higher form symmetry or subsystem symmetry. So for example, I can have a fermion system where I preserve fermion parity on every individual plane, or even some fractal shape. And the claim is that I can always dualize this into some spin model. The spin model will have some very weird gauge theory that allows me to have particles that behave like fermions but are still fractal. So for example, I can generalize Haah's code to have, so for those who don't know, Haah's code is some weird spin model where excitations can live only on the edge of the corners of this weird fractal. So instead of having this being a boson like the original Haah's code, I can create a twisted Haah's code where these are fermions. So I haven't explained what that means for that to be a fermion, and I don't have a good answer for that right now, but I'll try to motivate why I believe that it's a fermion. So, any questions about that?
There are also excitation on all those fractals, except they are not fermions.
So to create this I need to act with operators on this fractal structure, and it'll only violate some terms at the corners here. So instead of a string operator, you create at the two ends of the string. You excite in a fractal shape, and you only get excitation at the corners of this fractal. So let me quickly go over this story of Fermionic duality and Jordan-Wigner duality, how it works, and then afterwards, so in this part, I was just sort of want to motivate how I get what the story, the conclusion of the story is, and then later on I'll switch to Blackboard and then try to explain how to show how to derive these dualities. So this is a quick review of 1D Fermionic duality. So basically what you want to do is you want to map ZZ to X and X to ZZ, and basically that swaps G to 1 over G. But actually, when you say that the Fermionic duality mapping is this one, it's not actually that precise, because at the level of states, you're not able to map every state from that Hilbert space to this Hilbert space. And that's because you have a product of ZZ, which all product to 1. And when you map that, since ZZ maps to X, you get that the product of X is 1. And this is a Z2 symmetry of this Ising model. So you're only able to map, so the Hilbert space here can only be Z2 symmetric wave functions. On the other hand, you also have that going the other way. And so on both sides, you can only map states that are Z2 symmetric onto each other. For the 2D case, there's something similar. What is that? So basically what you do is you map X to Z, a product of Z on every edge, and then you map two Z's on a vertex to an X on the edge. And what happens is that you have a constraint, which is since, for example, all these terms, when I product it over the 2D space or a torus, I get 1. That realizes that the product of X over there is 1, and that's zero form symmetry, which is global symmetry. On the other hand, the product of Z over on edges on a closed bucket is equal to 1. So when I map that over, I get that the product of these X's is 1. And also there are non-local mappings, which is the product of these Ising terms over a whole line is 1. So when I map that over, I get that a product of X is 1. And so the constraint over there gives me a zero form symmetry. However, here I get a 1 form symmetry, which is that the product of this loop or this non-trivial loop going around the torus is 1. So it constrains my Hilbert space and says what states I am allowed to map under this. So often people like to say that when you do a Fermionic duality, you get the Tor code. I think it's more precise to say that you can gauge a Z2 symmetry to get the Tor code. That's a different duality. The only thing that it says here is that this Z2 theory on the vertices, when it's symmetric under the zero form, is dual to this theory, which are for states symmetric under a 1 form symmetry. Yes?
I think sometimes when people talk about Fermionic duality, it's richer than what you described.
Yes.
So you can describe
a different
also,
version.
so you can also consider, in other words, it includes not just the states in the Hilbert space satisfying this constraint, but the Hilbert space that relax this constraint that correspond to inserting some defect points.
Right. So if I add gauge fields here, then I can do a duality to the full Tor code. But I will not be talking about that duality today. So just to make clear what I mean by Fermionic duality in this talk is just at the level of duality. Of course you can do that, but it's more subtle, and I don't want to bother with the nuances. So let me stick to this duality for this topic. Okay, so the Jordan-Wigner duality in 2D actually has a similar story, and it's only been realized recently. So what you can do is you can have a fermion system with a fermion parity, and instead you can have hoppings between two sets. So what you want to do is you want to find an algebra of Pauli operators that has the same duality as this. And it turns out that if you choose the following, then you can convince yourself that these two have the same algebra. So for example, if I have gamma and gamma prime here that hops one fermion to here, and this one, then these two commute because this is a gamma, but this is a gamma prime. But for example, if I move it down here, gamma and gamma prime, these two operators don't commute. And that gets mapped to this operator, dx, and then this operator, x. And you can see that they share x and z, which anti-commutes. So you can check that all the other commutations will work out. And so you can map these set of operators to these set of operators. However, so similarly, you also have a gauge constraint. The constraint from going that way is the same because you can map these z's. The product of them is 1. It gives you a fermion parity, a global fermion parity on that side. However, the constraint going this way is sort of weird. So you have to multiply these hopping operators around the plaquette, but then not all of them cancel out. So here, gamma prime cancel out, but this one, gamma and gamma prime, doesn't cancel out. So that's sort of up to a phase, that's fermion parity. So I need to add an extra fermion parity here. The resulting gauge theory is weird. So instead of having just a plaquette of x, I have a plaquette of x attached with a vertex of z. So in the Tor code, you can think of that as sort of like a flux attachment. So instead of just exciting an E particle, you must always excite an E and M together. And these are hopping operators. So these Majoranas hop fermions, but here they also hop fermions because whenever you hop an M particle across the plaquette, you also need to hop an E particle across this vertex. So they must go together. So it sort of attaches the charge with the flux, and that gives you this modified gauge theory. Now we know that the plaquette term and the vertex term are just in the Tor code. This is just the product of those two. So in the ground state of this theory, it's just the same as the 2D Tor code. But however, this gauge constraint, along with this non-trivial one, is anomalous. So it's a one-form symmetry, but I cannot gauge this one-form symmetry. So basically, there's some notion of having an emergent fermion in a spin system to having this anomalous symmetry. So that's the example in 2D. So any questions?
Great.
Yes.
I probably missed something about the second arrow on the right hand side.
Yes.
What are you trying to emphasize?
I'm saying that there's a gauge constraint
Right.
induced from mapping operators here to here. So there's a certain product of operators, which is these hopping around a plaquette, that is equal to 1. And that induces that on the spin side, you need to have that this operator must always be 1. And you can think of it as a certain one-form symmetry.
And on the left hand side, you need just 2 parity operators.
Yeah, because I have gamma and gamma prime, so this doesn't cancel. So in the Kramers-Wanier case, it was just z's, and the z's all cancel around the plaquette. But here they don't exactly cancel, so I need to put in an extra p here to cancel. And I think that gives me some weird constraint.
Can you explain a bit the right hand side?
Yes.
Why is that?
Oh, so basically that's a plaquette term attached with a vertex term. And that sort of makes an E particle always attached to an M particle.
You can choose to attach on. on any of the corner. Or
Yeah,
there's
well,
a choice. You choose on a certain corner.
Yeah. There's a certain corner which comes from how I chose to map the operators here. Yeah, but that feature is not that important. Okay. Any other? So this talk will end very early if I just say, okay, now let's do it for x cubed, and here's the answer. You can choose to map Fermion parity to such object, and here the edges are Pauli z's, and I can map a set of 4 Majorana operators to some weird operator here, and you can check that everything works out. So if I said that, I would only need half an hour, but what I want to explain later is how to sort of consistently derive this and how to show that you can always construct such a dual model for if you assume translation invariance. But now let me get to some interesting things about this model, which is so.
It's also okay to give a half hour talk.
No. So for this twisted x cube, if you do the same exercise, the hopping operators are these, and from that you can multiply them to get a certain gauge constraint. So usually the usual x cube model has this term of a cage of Pauli z, and it has only these red terms, which are the cross term, of x's. However, this gauge constraint is now modified by some Pauli z's, and what that results is that if I have this gauge constraint, then the usual operator that excites a fracton in the x cube model, usually that's just this red line, it doesn't commute with these gauge constraints. So it has to be modified to these weird hopping operators. And what that does is that it makes the fracton excitation in the x cube, in some sense, become a fermion. Because this maps exactly to these 4 Majorana operators. So let me show you something weird that doesn't happen in the x cube that happens in this model. So for example, if I have, let me consider the certain process. So from the vacuum, I can excite 4 operators, 4 excitations. These individually are fractons. I can hop this one down here, and then I can collapse the top cube down into this one particle. And then in the end, I annihilate everything. And if I do that, what I get is a minus sign. And that doesn't happen in the x cube model. So in the x cube model, that process would just be a plus sign. Let me show you again. So I create 4, and then from this 1, I branch it into 3 more. I collapse this 3 into 1, and then I collapse this away again. So this gives me a minus sign. And that's because I'm acting with 4 Majorana operators here on this plaquette and on this plaquette alternate. And they share 1 Majorana here, which anti-commutes. So that gives me an anti-commutation sign. So that's what happens in this twisted x cube model that doesn't happen in the usual x cube model. So another similar example is in this. I can construct similarly a twisted Haah code, where instead of I can create 4 excitation which has the same algebra as Majorana operator. So if I create 4 of them, I move 1 of them down, I collapse 3 to 1, and doing this again, then this gives me a minus sign. So this sort of seems to suggest that there should be a certain grading process that you are able to check whether your excitation is bosonic or fermionic, although that is still work in progress, and we're still trying to figure out how to precisely do that in general systems.
So in this case, you don't expect there to be some co-cycle that implements the twist?
At least it's not clear what the data is, because for these subsystem symmetries, people have no idea what generates the twist or how they're classified yet. Right? right now.
Yeah, it's not complete algebra anymore.
Yes. So I hope that's convinced you to listen to the rest of my talk right now, which I'll try to formulate how to get such twisted models.
By the way, for Ivan's question,
Yes.
like for subdimensional system symmetry, even though you may not be use the normal group homology like cocycle in that dimension to classify them, but you can relate them to some. You can still relate them to some form of a cohomology group, but you know the work.
Right. So Cuban has a paper on that.
That it will be some cohomology group. Let me see. For example, in let's
For
say
subspace?
yeah. For example, it's 2 plus 1. They usually use H3 cohomology group. But it turns out that you consider subsystem symmetry in 1 plus 1D dimensions of a 2 plus 1D system. You will need to use some cohomology H2. 爬到some H2 of some just H2 models on H2. There's some larger group. Sorry, H2 of some due to some power on the numerator and the models on H2 some denominator.
Right.
Still related to some maybe some group homology in some way, but
Let's say for fractal, people have no idea how to do that. So, okay.
generally people don't know the mass structure.
Okay. So, what I want to do the rest of the talk is to sort of how to express. I want to go to some simple examples in 1D and 2D to how to write down Fermionic duality and Jordan-Wigner duality, assuming translation using some algebraic formalism, which John Haah has proposed. And this sort of allows me to show how to construct such a duality in general, even for like fractal cases or subsystem cases. So I'll want to switch to Blackboard. And then if there's time left at the end, I will give you some more interesting examples on slides. So this algebraic formalism was developed in this paper, and so I guess I need to apologize for Sargar that he will probably be bored for the next half hour. But, so what I want to do is suppose I have a d-dimensional cubic lattice with spins on the vertices. What I can do, suppose I fix an origin, then I can label an coordinate. So for example, I1 to ID, I can label that as some monomial, x1 to the I1 and times xd to the ID. So for example, if I have coordinates 2, 1, 0, then that I can write this as x squared y. And because the reason I want to do this is that I want to be able to write down a general Pauli operator on this cubic lattice in terms of a polynomial. So the notation is that I want to label it with Pauli z, the position of the Pauli z, and the position of Pauli x. And the position of Pauli y is where, since y is just z times x up to a factor, I can express any Pauli matrix up to a sign with this notation. So I'm going to label it as some vector. For example, if I want to label z, Pauli z located at the origin, then I just put a monomial 1 here, and then let me put a line here to say that the top part is Pauli z and the bottom part is Pauli x. Here I have a 0, which means there are no Pauli x's. So if I have x at the origin, that would be 0, 1. And if I have a y at the origin, that would be 1, 1. So for example, if I have an Ising term z0, z1, let me say I'm just in a 1D lattice, then I can write that as 1 plus x. So 1 here is the z at the origin, and x here is z, move one side to the right. So the nice thing about this is that translation is naturally written as multiplication. So, for example, if I have this Ising term z0, z1, I want to move it one side to the right, then I just need to multiply it by x. So if I do that, I multiply this vector, so I will get x plus x squared. So x is one side to the right, and x squared is two sides to the right. So this x gives me an action on this vector and it translates Pauli's. So mathematically, what I'm doing is that the polynomials live in a certain polynomial ring, which is, since I only label whether they're present or not present, I can label them by the polynomial ring F2. And F2 has these x's, y's, and z's. That's like x1. But I also need the negative coordinates. So this is the polynomial ring. And so any polynomial here lives inside this polynomial ring. And the action of translation acts as multiplication on this vector. So actually, let me write this as R. It's a certain ring. So the action of translation on this vector actually just gives me the structure of a module. So any such object in here, I will say live in a P, in a module P, which I'll call Pauli module. So basically, what this object is, it describes a general operator, general Pauli operator on a cubic lattice. And I can act on multiplication to implement translation. So in general, I might have n sites per unit cell in some cubic lattice, and any lattice I can rewrite it in some way as a cubic lattice with n sites per unit cell. So in that case, what I want to do is, if I have n sites per cell, then I'll write it as a length 2n matrix. So the first n tells me where the z's are in each site. And the second one tells me where the z's are, and these are where the x's are. So from this, the next step is how to calculate commutation values. So we know that the Pauli operators commute up to a sign. How to compute that? It turns out that you can compute, suppose I have two operators A and B, which I represent as in this polynomial language. I can compute whether they commute or anti-commute with a certain inner product. So this inner product is defined as a dagger. So dagger here means that I transpose the matrix and also send x to x bar, which I define as a notation for this x inverse. So I invert the map. And this lambda is a symplectic form. So in general, there's supposed to be a minus, but I'm working in 0 and 1, so I don't care about the sign. So basically, why does this work? I'm sort of swapping z's and x's, because if I have two polynomials, they anti-commute if the z's and x overlap. So I want to count how many z's and x's overlap. And I can do that by comparing this polynomial up here with this polynomial down here, right? And vice versa, and I add them together. So which is why I need to swap them, which is why I need this matrix here. So let me give you an example. So suppose I have, let me define this big X to be the transverse field of a 1D Ising model. That's 0, 1 over there at 0. And let me define this big Z. Maybe it should be the fold so that's not the Pauli matrix. It's 1 plus X 0. That's Z0, Z1 gets equal to X0. So what's the commutation relation of these two? So I can compute this inner product. That's 1 plus X bar 0. Have this matrix. And then I have 1, 0. And that gives me 1 plus X bar. So obviously, they don't commute. Where do they not commute? X naught. So it tells me where the positions of these operators that doesn't commute with this operator. So for example, this is telling me that X naught doesn't commute with this Ising term at the origin. That's correct. They share an X and a Z at the origin. But also, this X bar is telling me that it doesn't commute with the one shifted one side to the left. Sorry. So if I shift this Ising term one side to the left, it gives me Z minus 1, Z0. It still shares a 0, Z0. So it anti-commutes with this X0. So with this, I can calculate if terms commute in my Hamiltonian or not, and whether and where they anti-commute. So what I wanted to define next is stabilizer map. So suppose I have a bunch of terms in my Hamiltonian that all commute. I can write a certain matrix where each column are an operator. So all these vectors live in P. So those are operators, and I'm just augmenting them together. Now, if all of these operators commute, it means that for every row sigma I and sigma j, that always can be 0. Let me just write that as a matrix notation. That is some 0 matrix. So if I have, for example, a stabilizer code, a Pauli stabilizer code, and all the terms commute, then it must satisfy this condition in this polynomial language. So what I want to say here is that this map, actually, I can formally write it as a certain map from another module G, which is labeled as the generator. So it just labels how so the objects in G live in here, and they act on this sigma. You multiply sigma from it. So here it's just labeling which terms do I use in my stabilizer. So for example, if I have a term here, I can also multiply with the term. I multiply with the term here. So this just tells me which ones to multiply together, and it gives me an operator in P, which is a Pauli operator. And furthermore, it's insightful to define. This is sigma here. It's helpful to define another map called epsilon. It's called the excitation map. So epsilon is defined as this like linear function if you want, or this language just the adjoint of sigma. So the adjoint of sigma tells me that whatever I plug into here, it'll tell me whether it commutes with sigma or not, because I'm computing this commutation value. So it tells me whether this commutes or not. So if I map this from epsilon to some other space, let me call it E. This is just some other module, excitation module. So if all the terms in sigma commute, it means that this is satisfied. In this language, it means that epsilon composed with sigma is 0. So stabilizer code is equal to that. This thing is a complex.
Sorry, can you explain about sigma again?
Sigma gives me the different columns of my code. So it gives me different columns mean different operators.
So sigma.
Different Pauli operators. I have a set of Pauli operators. I just
Yeah.
put them together into a matrix.
Yeah.
Yeah.
Then sigma acts on like.
Sigma is a map from certain. Let me give an example. Yeah. So in the 1D Ising case, suppose I have only 2 of them. I have only 2 operators. I have a transverse field and I have Ising. Then I can construct sigma as I take z, I put it with x, I add joint, add. Then that's 1 plus x, 0, 0, 1. So then I can choose in my Hamiltonian which terms do I want. So for example, if I act on with 0, 1, then I only pull out the Ising term, the transverse field term. Right. If I act with 1, 0, it pulls out the, so it just labels which one. But I can also do like, I can have them together if I want. That would give me like, this would be like 1 plus x1. That's just like g naught, g1, and also x naught. And it's an allowed term of my Hamiltonian built from the Ising term and the transverse field.
And what is G? So G is.
So G is just labels which Ising term I want to add. G, the objects of G just label which Ising term they want to add. So if I add 0, 1 in G, then it gives me the.
And if you say 0, 0x or 0x squared,
Yes,
you
you
get
0x. Then it gives me a transverse field translated to the right.
at the like 1 point. Yeah. So G is just set up
Where I want to
n
put
by
my stabilizer.
n by 1 column with entry the polynomial.
Yeah. Okay, yes. So now, actually, in this case, it's not a stabilizer code because terms don't commute. So in general, so this was what Haah used in his to analyze stabilizer codes. But in general, it also works even if sigma contains terms that you can still do stuff with it. So let me change this word stabilizer to just be something like Ising map. So I'm allowing terms that don't commute anymore. So this won't be a complex anymore, but it turns out that we can still say some stuff about it. Any other questions?
Excuse me.
Yes.
The reason you present this is because this will help you to
Generalize.
understand your model.
Yes, it'll allow to do like Jordan-Wigner. I'm going to explain Fermionic, how to do Fermionic in this language.
Yeah.
And then for Jordan-Wigner, it's very similar.
And the way you derive your model is
It's just
based on
this. So you can just churn out models by doing this. So let me say it. Let me write down generalized Ising model. So I'm going to have some Pauli operators, which are transverse fields. Let me call that some old x. And in general, I could have many sites per unit cell. So in general, it could be like some identity matrix here instead of just one. let me just focus for the 1D case. For the 1D case, it's just one side per unit cell, and I have a Pauli X here. I can also have some Ising terms, which I'll denote by a bold Z. And this Z could be anything. It could be, for example, it could be the usual Ising model. So for the usual Ising model, Z is 1 plus X, 0. If it's 2D, then I'll have two terms, one on the X direction and one on the Y direction. But in general, you could have like Ising terms that have Pauli X's in them as well. That's totally fine. The only requirement, the thing I require is that the Ising terms should all commute with themselves. And it shouldn't commute with the Pauli X. That's the only thing I require. So what I require is the transverse field, I find a basis where they all point into the X direction. And I write whatever Ising terms I have. They need to all commute, but they don't commute with the transverse field. So that's what I define to be my generalized Ising model. So we can check that this thing, this thing is a matrix. It's like
So this is not a stabilizer because sigma I sigma j doesn't become 0.
sorry.
So this is not a stabilizer because sigma I.
Right, because it's an Ising model there.
Sure.
So sigma here is just I put Z and join it with X. And if you work out what this is, it turns out, let me just skip bold symbols for now. This is X, Z, X. So these two are 0. These are just transverse field, they all commute. These are the Ising terms, they all commute. But this matrix is not 0. Yes?
How do you impose some constraint here, like some product from everything equal to 1?
Oh yeah. Later I'll. Right. I'm about to get to that. So here I'm just saying that this is an Ising model because it contains terms that it's not 0. This matrix is not 0. I'm going to refer to this as some commutation matrix. So instead of just doing pairwise, I'm just doing it with the commutation value. This is now some commutation matrix. So what do I mean by a symmetry of the model? So a symmetry of a model is a product of some operators which, when I apply to the Hamiltonian, doesn't excite any terms in the Hamiltonian. So it means it's an operator in P which doesn't excite anything, which means under this excitation map, it gets sent to 0. So symmetry is just kernel of epsilon. What's the kernel of epsilon in this example? So I need to compute epsilon. I need to sort of flip this over. So for example, in the 1D Ising model, sigma is, I think I wrote that already, 1 plus x, 0, 0, 1. And epsilon is, did I write that down? No, but I think it should be, so I diagramed it and then I applied this symplectic. I joined it. What's the kernel of this? Turns out that if I multiply, so I want something that gets sent to 0. This 1 here comes from the Pauli X. So here I cannot have any Pauli Z, right? Because nothing here, anything I put here will not get sent to 0 because I'm just multiplying with 1. It has to be 0. And now this thing, this is 1 plus x. I can telescopically collapse this if I put an infinite sum. Right? So this thing is in the kernel of epsilon. This is just the global Z2 symmetry line. Ising model, right? It's just product of x over all sides. This is kernel of x. Okay. Any questions? Okay, so let me state what the Fermionic duality is. What I want is, I want to find another Ising model. Let me call it sigma tilde. I also call it dual Ising model from time to time. I want to find a dual Ising model such that it has the same commutation relations as my original Ising model. Meaning
X bar is X inverse?
X bar is X inverse, yes. So these are the commutation relation where they commute, where do they commute or not, where do they anti-commute. It's all encoded in this commutation matrix. I want to find another model which has the exactly same commutation matrix. What that means is I want a particular model such that I have another polynomial p tilde. It could be a different Hilbert space, so I put a tilde on it. What I want is so sigma, this is actually epsilon, this excitation map composed with sigma. So that's just this map. So I wanted, having a duality means that I want this diagram to commute. So claim this at this point this is not specific to Kramer's one. Yeah. So maybe I should just say here duality. But the Kramer's one has a particular choice of that. So sigma was originally, I have z and I put x. I will now have a sigma tilde, which is x tilde, z tilde. So what it does, it swaps the role of the transverse field and the Ising term, and it's defined as, so x tilde is 0 identity, and z is given by this. So if you plug that into that and you compute this inner product, you can check that it's equal to this original inner product. So let me give an example for that. For this 1D Ising case, the 0 Ising, I have this sigma. So I have my transverse field. So x is 0, 1. It gets sent to, let me do z. Ising term is 1 plus x 0. It gets sent 0, 1. And this is x tilde. Now z tilde will be z, this inner product z of x. So inner product of z of x is 1 plus x plus. So I get 1 plus x plus 0. So that's my Kramer's one duality. So I map Ising to transverse field to Ising. This is 1 plus x bar. But it's still, if I just shift it by x, it goes back to 1 plus x. So in 1D, everything is self-dual.
Why is there a reason you take it as the inner product of c and x? Did you explain that part yet, or?
Yeah, it's sort of like
to make sigma inner product.
right. So what I'm actually doing here is that I sent my Ising term to a transverse field living on the link.
Yeah.
To get this, now I want to send x to some z, to get the commutation correctly, I need to check where these anti-commute so that I can put the z's correctly. So I want to know where these originally anti-commute. So that's where I just set this to identity and I figure out where else to put the z's to make it match.
Just come from looking at the commutation matrix of diagonal component.
Yeah, I mean it just comes from the sigma tilde is sigma sigma.
Yeah, I want this, and I claim that this is a valid choice. And
But once you choose x tilde, it's only valid choice for z tilde is given by that.
Well, the bottom component can be 1. It doesn't fix the
bottom component.
It doesn't fix the 0.
Yes, yes. So it's a certain choice. That just means that after I do a duality, I'm allowed to do something else that preserves the symmetry. I can still add one. Yeah, but I'm choosing a particular choice.
Also, it's also it's further constrained by symmetry.
Yeah, so there's a symmetry here also. For epsilon tilde is the dual symmetry. And but in this case, since the operators just map back into each other, the symmetry is the same. But in 2D, 3D, it can be different. So you can get one form just by reading out what this map is.
So basically, but to match the symmetry, can matching the symmetry give additional constraint?
Matching the symmetry.
I don't know.
Well, I think he was asking, so in principle, the z, for z tilde, the bottom component can be, for example, 1, right? Still satisfy this commutation constraint. But he's asking whether imposing symmetry would fix that ambiguity to be 0. That's what you have chosen.
Not necessarily, I think. For example, I could have sent this to YY. That's totally fine.
Yeah.
So I could have made these two down here identical, up here and down here identical. Yeah. Just choosing a particular choice. So the last thing I need to mention is that this symmetry, I said before that it's induced by the product of operators in the dual that product to the identity, right? So for example, if I have these bunch of z's, they all product to the identity, that should map to x being the identity. How to say that mathematically? I want to say that whatever, so things that product to identity, for example, here are in the kernel of sigma. So I just want to say whatever things product to identity. I dualize it, meaning I send it through sigma tilde. And the claim is that this is exactly equal to the kernel of epsilon. So the inclusion this way is actually obvious from commuting diagrams. It doesn't require me to know anything about this map I chose, because kernel of sigma lives in here. I push it to sigma. I want to show that's in the kernel epsilon tilde, but the diagram commutes, so you can go this way. But the other inclusion requires this choice. I'm not sure why it works, but you can show that the other inclusion holds when you assume this. So it's not just that the product of these, generate these, they're exactly equal when I choose this. And also, in this case, so the other is also true. The thing with product to identity exactly generate the symmetries of the dual. Okay. Good. Any question? I think Kramer's one here. It's down here, so any questions up as well? So now, Jordan-Wigner. It's a very So just hopefully you don't need to erase anything here, but let me add that for fermions, instead of using x and z, there's a similar algebraic notation, which is for a certain complex fermion, I can break it into two Majoranas, gamma prime, the real and imaginary parts, and I have a fermion parity, which is this. And so I can represent a real any fermion even term as a polynomial. So instead of putting where the z's and where the x are, I put where the gammas and the gamma primes are. So for example, fermion parity up to a sign would be in this notation 1, 1. And suppose I have a T-type chain. I have this hopping gamma prime gamma. Then let me call a general term like this S. So P will act the role, the Fermion parity will act the role of the transverse field, and S, this hopping, will act the role of the Ising term. So S in this case will be in this notation. Here I choose gamma to be at 1, and gamma prime is at one side to the left.
So in the Pauli notation, x squared is identity, but in a fermion gamma squared is 0.
Gamma square is 1. Gamma square is 1.
Ah, okay.
Okay. So instead of generalized Ising model, let me say generalized Fermion model if you want. I change this to Fermion parity. This is P. That's 1, 1. And I change this to be some interaction term. So in general, it doesn't need to be hopping. It can be 4-body if you want, 6-body. And replace this with S. And it satisfies the relation that it doesn't commute with fermion parity. And well, fermion parity commutes with itself. But the difference is that these interaction terms doesn't need to be 0. For example, in the 2D Jordan-Wigner I showed you, we had gamma and gamma prime, and these two did commute. So unlike the Ising terms, they don't need to commute. I will not require that they commute. So now you can define a similar map where I just take this to be S, T. Let me just label this fermion. Now the commutation relation is a bit different. Originally, my commutation relation was using the symplectic inner product. Now, for fermions, let me put an F here. It's an orthogonal inner product. So that's all you need to change. Why is it orthogonal? Because you have gamma and gamma primes. You want to check where they anti-commute. So you check where the gammas overlap and where the gamma primes overlap. That actually commutes. But you subtract it out of the total anti-commutations when you move them past each other. That's why it counts the number of anti-commutations. So for example, I have gamma 1, gamma 2, gamma 2, gamma 3. commute, but I move this, you're supposed to get 4 anti-commutations, but gamma 2 actually commutes, so subtract 1. Everything is mod 2, so I can just count how many overlaps of gammas I have. That's why it's this inequality instead, which I put with an F. So F means orthogonal, but F here means fermion. Right. So this sort of just changes to, I just replace X with P, I replace Z with S. But now this one is not 0. This is the only one that's 0. Fermion parity is commutes. That's the only one I set to 0. Okay. Now, so similarly, I can define some map. I've changed notation from Pauli module to Majorana module. That's just a renaming. There's nothing much different. And this excitation map now doesn't have a lambda. It's just the usual. It's just the adjoint under the orthogonal norm. Okay. So now I want to do duality, and duality now becomes, I change this to an M, this is Majorana. So I have some map of Majorana. I want to find a Pauli that has the same commutation relations. So I just change all these to F. Okay. So now here is the map. So I map from S to P to X and Z tilde. I need to change this to P and S. The only thing different is that I told you that S, the hopping operators don't need to commute. So in general, if I just map it to this doesn't work because all of the transverse fields commute. I need to modify that by some other matrix here. I'll call it T. And it turns out that if I can find a T such that this holds, then I want just this T to replicate the commutation relation of the hopping operators. And it turns out that this condition gives me the right algebra. So what this does is that the hopping operators, when you do Kramer-Wanier, I just map it to X. But then in the Jordan-Wigner, you need to remember that I map like gamma and gamma prime to something like X with a Z attached to it. So this is what I'm attaching. I'm adding this matrix T up here, which are Pauli Z's at some positions. So that's basically what I'm doing. You add these Z so that they have the right commutation relations. And as long as I have this relation, then I found a dual. So
there are T that you can solve.
Yes.
There are many possible T.
There are many possibilities.
And you just find any T.
You just need to find a T. I call this T a transmutation matrix because it sort of transmutes the excitation from being bosonic to fermionic. Because of these hopping operators, you can do certain moves that gives you minus sign. So that's why I made it T. So now I'm going to throw out a couple claims. T exists. And the easiest way to see that is this matrix is symmetric. So I can always find some other matrix such that this plus its permission is my symmetric matrix. So in particular, if I have such a matrix, this is my S, I can just construct T as some upper triangular matrix where I just choose the top half here and I choose half of these half of the diagonal and put it here. Just choose arbitrarily. So T always exists. I can construct it exactly. Right. So you mentioned a good point that T is not unique because I can always define another T prime which is T plus A, where A is symmetric. That still satisfies this relation. What that means is when I choose to attach these Z's, what was the map?
Minus.
Sorry.
It's minus.
Oh, it's I'm working in the field F2. So for example, when I chose, what was the map? I map this to Z and X, and map this one to Z and this X. If I modify this by a symmetric matrix, or anti-symmetric, it just means that I'm just moving one of these down here somewhere. So it means I just reattach this Z to somewhere else down here to get the same anti-commutation relation. So I just move a Z here to, what do I do in this case? This one comes because this line anti-commutes with this line. So then I can just move this Z here, which still, yeah, maybe maybe here. So action of a symmetric matrix just moves where the Z's like. Now, it turns out that if you do this, if I change T by a symmetric matrix, the resulting gauge theory, or the kernel of this epsilon tilde, which is the symmetry, the dual symmetry, would change. But you can show that it always changes by a finite depth Clifford circuit. So, in particular, that circuit is some control Z's, which if I conjugate the Z, it gets rid of the Z here and puts it back up here. So, yes.
Sorry, so by symmetric theory, do you mean symmetric or you mean Hermitian? Are the X, conjugated?
Sorry, yes. I meant it to be the same thing, but yeah, I can say Hermitian for now.
Okay. Because that's different.
Yes, sorry. Hermitian. Yes, so even though I get a different gauge constraint, I can relate it back to a gauge constraint with a finite depth circuit. And so it gives me the same dual theory. The last thing is,
Symmetry.
yes,
Not the same.
sorry,
Symmetry. We shall not the same.
yes, sir. Let me say Hermitian.
Okay. Unless you choose A to be real.
Yeah,
You don't.
let me just say Hermitian for now. Yes. So the last thing you might wonder is, I've chosen this to be gamma and gamma prime. I could have chosen this to be just gamma, both of them. I would need a new algebra to describe this. But this basically means I attach a fermion parity to change gamma to gamma prime. In general, I could have defined an operator where I attach fermion parity here or here. I can attach it anywhere. This is my new hopping operator because this does nothing to the fermions and it just hops here. But I can show that the resulting dual symmetry is invariant under this. So what I mean is that under this hopping matrix going to itself plus fermion parity times some polynomial where the polynomial tells me where I attach these. The kernel is invariant. I haven't been numbering them properly. So in some sense, it shows that this duality, this Jordan-Wigner duality is well defined. It exists. It's in some sense unique under up to basis transformation of how I represent them. Yes.
So I missed the first part of your talk.
Yes.
So the duality, do you have a, I mean, the Lagrange derivation, or where you get the duality relations?
Where do I get this?
Yes, for the t plus t.
Oh, so you want to check that these have the same algebra. That's this relation.
Okay.
And if you plug that in, that gives you this relation.
Oh, this is your derivation.
I assume this form, and I plug it in, and you find that if this can be satisfied, then then it has the same commutation relation. Oh, and then lastly, this generalizes. So, you can prove that it still holds. So all the symmetries are generated from what product to be edited.
But this one really looks like t duality. The relations.
Uh,
If I give me a gauge theory, I can. I don't know.
Not sure about that connection right now, though. I won't talk to you about it.
In 1 plus 1 dimension, in certain cases where it gives you 2, I hardly mentioned there's no so it's general.
So I guess I have.
You're talking about generalized Jordan-Wigner.
Yes. Yes.
Is generalized Jordan-Wigner right to T duality?
This is more like going from fermion to boson, so you're summing over string structure.
Mhm. Yeah.
The primary one here is right. In 1 plus 1.
Right. You can think of it as summing over spin structure and integrate out the fermion. That's not quite captured here, at least. Let's see. I have less than 10 minutes left, so let me just bring the.
Yeah. I mean, is there some formula like this for the Kramer-Wigner? Generalized Kramer-Wigner?
Oh, that's the one I said before. When I said Kramer's one, I meant generalized already.
What's the formula? Is there some final constraint? Like?
No, there's no constraint because I demanded that all the Ising terms be. So I don't need such a constraint.
There's something you can write a formula that bugs it.
Well, for the Kramer's one here, it's this. So this all commutes, and this is 0. That.
All right.
Yes. So I have a few minutes left, so let me just splash through some examples really quickly. So one example you can consider is a fermionic system with one form fermion parity. It means I conserve fermion parity on every closed membrane. If you do the duality, you get a weird one-form gauge constraint. But this gauge constraint, the ground state of this is just usual 3D torque because it's the usual vertex term attached with plaquette terms. But what I'm wondering is whether this is anomalous or not. It might not be anomalous, but if it is anomalous, then it should match with some SPT default. So if it would match anything, it would match this SPT, although I have no idea whether that's true or not. So that's some further thing. So I will just mention that from this program, you can generate a plethora of dualities, and you can play around with all of these games. And let's see, which ones do I like?
And how did you know whether symmetry is anomalous or not in your table?
Whether it's anomalous,
Duality?
for some of them,
yes,
they're known examples.
Known example.
Yes. For these yeses, I have no idea. I think they might be.
Why would you put yes?
What? There are some indications of for example, the x cubed, there is some process I can do where I can get a minus sign, where it's not possible in those. So there should be some relation between, we don't know whether they're fermions or not, but we shouldn't be able to condense them. And that would be related to whether this thing is anomalous or not. But I put a question mark here because I don't know. I also don't know whether these models, these twisted models, are the same phase or not, so I also put a question mark. They might be a different one. For example, in 3D, the twisted 3D torque code is Fermion. So put an F up there. I don't know whether these ones are. For some of them, I can show that they are.
Sorry.
So you can do, yes?
Your question was, how do you know the Z2 are anomalous? Is that your question?
Yeah, if you
using,
want a
because
rigorous
I was wondering whether you somehow figured yes question through, whether you diagnose something through this duality.
So when it's no, I can say when it's no. It's no when I can find hopping operators that commute. If this is the case, then I say it's no.
Why?
Because it just bosonizes to things, operators that are bosonic, everything just commutes with each other. So you could ask for this one, say the 2D torque code, whether you can find, whether I can attach fermion parity somewhere to make everything commute. The answer is no. So it's anomalous. In some cases I can find where they commute. And these I couldn't find. And I don't know how to exhaust all the possibilities, so I put a question mark.
So duality really diagnoses something.
Yeah, it's not an exact statement about anomaly, but it's just some, for these question marks. I can say exactly when it's no, but yes, the examples where people know, but the question marks are open questions. Yeah, let me just skip the line cases. They can be lines. You can have fractals if you want. Let me just mention one interesting thing about getting new codes for quantum information people. So the thing I did is I took some Ising model, I replaced X with Fermion parity, I replaced Z with Majoranas. And what I did is I got a Fermion model with some hopping term. I can do a Jordan-Wigner to get some model. But here actually you can start from some CSS code that you like. You ungauge it, you get an Ising model, and follow through this procedure, and it should give you a twisted model, hopefully, if you cannot find hopping operators that can use. So if I put here the x cube, this can be twisted x cube. So a fun example is actually, I can choose this to be a Majorana code. So for example, in Sarkar's paper, there are a bunch of Majorana codes, such as the Majorana checkerboard model. I can choose my CSS code to be a doubled CSS code, which is for a certain, for example, if this is the Majorana checkerboard, this is the Pauli checkerboard. And I can ungauge this, I get some Ising model, I write a new Fermion model, and I gauge this, so I get a twisted checkerboard model. But it turns out that for this, if I choose this particular choice, I can also do the Jordan-Wigner on the Majorana code. So it gives me a bosonized Majorana code. And because we know that these two are different phases, this is a trivial fermion, this one has some fracton order, this should also be different. And since these ones are very similar, you get a new Majorana code that is distinct from your original CSS code or your twisted stabilizer. So it's sort of like a new game you can play to generate new codes. So the example I gave is for this Majorana checkerboard, that's Pauli checkerboard. So you would get a new bosonized Majorana checkerboard, which I don't know what the properties of this model are. It's a fraction. Those are open questions. So let me conclude. I have exactly 1 minute. So what are the open questions from this program? I have fermions that are fractons. I don't know how to grade them, but hopefully we'll know soon. We're trying to work that out. And whether the ground state of these twisted models are distinct topological phases. Are there top anomalies corresponding to these fermions? If there are, what are the SPTs that cancels this anomaly in one dimension higher? In general, I can have a spin system with emergent fermions. But right now I have no idea how to fermionize it back. I can only go one way. I only know examples where I've already bosonized it. But given the general, like Levin-Wendt fermion model, how do I fermionize it? I don't know how to do it. It sort of should be related to some anomaly matching of this theory. But so we need to classify what such anomalies can exist. And for these SPTs or these actions, these anomalous actions are related to Steenrod squares. One thing I told Laura was I assumed that there exists some spin structure, but you need to generalize into these cases. How do you talk about these Stiefel-Whitney classes or when they're fractal or something like that? That would probably need some work. I assume translation. How do you do it on a general lattice? I don't know yet. And also, can there be SPTs protected by these fermionic higher form or subsystems SPT that require no other symmetry? I don't have any examples for that. And then lastly, I can generalize this duality from fermions to parafermions. You just replace this F2 with Fn. So if that's possible, it's straightforward here, but if fractons can be fermions, can fractons be parafermions? It seems like an interesting question. So, perfect timing.
Thanks, Nat, for perfect timing, perfect talk. So we should have a perfect ending by asking perfect questions. Any questions? Well, if not, let's thank Nat for asking. Thank you. It should be on time, but that's.
Yes, we already did that.
That's wrong.
I was going to ask about